All right, hello everyone, and welcome back to this series of astronomy talks. So I apologize that this video is going up a bit late. I made an earlier recording, but it got very laggy towards the end, so I decided to redo it. Tonight is the last talk about this solar system. We have talked about the terrestrial planets in quite a lot of detail. We've talked about the gas giants, their orbiting system of moons. Tonight, we're going to talk about all the small stuff that we sort of ignored along the way, the asteroids, the comets, and the dwarf planets. But before I get into all of that detail, first, of course, we've got to do our little quote for tonight. And that is by Freeman Dyson, unrelated to the Dyson Vacuum Company, I believe. But his is a very beautiful quote that goes, "As we look out into the universe and identify the many accidents of physics and astronomy that have worked to our benefit, it almost seems as if the universe must in some sense have known that we were coming." So now, before we get into the physical aspects and the orbits and whatnot of these three different types of objects, it's helpful to understand a little bit of the history of our understanding of these three types of objects. And we'll start with the asteroids. So the word asteroid comes from a Greek word meaning star-like. Aster meaning star, and oid is like. And that's because in our early telescopes, as we started to discover these asteroids, they appeared like just points of light, just like stars, except of course they moved, unlike the true, much further away stars. That first asteroid was discovered just shortly after the discovery of Uranus, only 20 years later, in 1801, by the Italian astronomer Giuseppe Piazzi. And that asteroid was the largest asteroid in the asteroid belt, named Ceres. Ceres was the Greek goddess of grain and harvesting. And her name is actually where we get the word for cereal from. So there's a little bit of extra etymology there for you. It was originally thought to be a planet between Mars and Jupiter. That is, of course, until more asteroids were discovered, such as Pallas, Juno, and Vesta. Those were the next three to be discovered. In fact, those are all also sort of considered planets. And so for a time period, just like today, we make our elementary school kids, our primary school kids, learn the order of the planets, Mercury through Neptune. Back then, when these asteroids were first being discovered, they were added to the list of planets. And so kids had to memorize, I think, at most 15 planets at one time. But as more and more objects were discovered in essentially the same area of the solar system between Mars and Jupiter, they realized that these aren't other planets. This is actually smaller objects in a much larger region called the asteroid belt, which of course we know all about today. Ceres is the largest object in the asteroid belt. In fact, it's so large that it is distinctly spherical. So that actually makes it a dwarf planet and not an asteroid. However, we'll lump Ceres in with all the other asteroids tonight for ease of talking about it. Nowadays, we know about hundreds of thousands, if not millions, of asteroids, and more are continually discovered each night. So it is truly a populous place. These are not planets. These are truly other small rocky objects. Moving outwards, we come to the comet. This also comes from a Greek word, this time meaning hair, because as a comet gets closer to the sun and it sprouts those beautiful long tails, that sort of looks like hair in the sky. And these are absolutely amazing to look at. And so they sometimes had a profound effect on human behavior. A very good example is the Chinese, who, whenever they saw a comet appear in the sky, they thought that was a sign from the heavens that the ruling emperor had lost favor with the heavens. And so some change was about to happen, usually violent change directed towards the old emperor. But they took the appearances of comets very seriously. However, despite both Chinese and many other cultures in the world ascribing great importance to comets, no one really came up with a good theory for explaining what comets were astronomically. Aristotle, his opinion held sway over much of Europe, and he believed that they were just atmospheric effects in the Earth's atmosphere, that they weren't true astronomical objects beyond the Earth. That is until the late 1500s, when the Danish astronomer Tycho Brahe, who we talked about many, many weeks before, made observations, actually measured the parallax angle to get a distance to these comets, and showed that these comets are actually things not just beyond the Earth, but beyond the moon as well, orbiting the sun just like all the other planets. Now we know tons more about comets. And we know that the vast majority of them actually don't come anywhere near the Earth, so they don't grow tails. Instead, they all sort of hang out in two different regions of the solar system, the Kuiper Belt and the Oort cloud, which are both beyond Neptune. And we'll talk about those in a little bit. And then finally, the dwarf planets. This is a very controversial category, especially for people of my generation. It all started back in 1930 when Pluto was discovered by the American astronomer Clyde Tombaugh. And Pluto was added to the roster of planets. It was called the ninth planet. Even in my early childhood, memorizing the list of planets, Pluto was always at the end. But as our telescopes got better and as we became more interested in the outskirts of the solar system, we started to find, just like with what happened to Ceres, we found tons of other things in Pluto's orbit. And so Pluto appeared to sit in the middle of the Kuiper Belt. But the real killing blow for Pluto was in 2005 when the Caltech astronomer Mike Brown, and yes, you can find him at Twitter as @PlutoKiller, he discovered Eris. This is an object in the same region of space as Pluto, but just a little bit more massive. So clearly Pluto doesn't dominate its orbit. There's tons of other things in it, including a more massive object. Eris was named for the Greek goddess of chaos and discord, and boy, chaos and discord did she cause. Her discovery really forced astronomers to actually confront the definition of planet. It didn't really have a good definition. We knew what the planets were, but defining the broad category of planet to encompass not just the arid worlds of Mercury and Mars, but also the gas giants of Jupiter and Neptune, that is a very difficult thing to do. And so in 2006, the International Astronomical Union finally got around to doing it. Now that vote in and of itself was very controversial. It was at the end of that year's conference where most conference attendees had gone home. So as opposed to the thousands or so people who would attend that conference, only 400 actually voted on this new definition, this new category that we call dwarf planets. Essentially, really objects that are large enough to be spherical like Pluto and like Eris, but they haven't cleared their orbit. That's the defining characteristic. They haven't cleared their orbit. They're not dominating that region of space. So it includes Pluto and Eris and a bunch of other small objects. In fact, here are some confirmed dwarf planets and some candidate dwarf planets to scale. So you can see Earth there on the right of the slide. And the dwarf planets here are Pluto, Eris, Sedna, Ceres, Haumea, Makemake, Gonggong, Meteor, and Orcus. And then I've got the three next discovered asteroids there at the bottom there for scale. Some of these dwarf planets are very interesting. Many of them have their own moons. Pluto has a system of 5 moons. Charon is the largest, but recently, in the late 2000s, discovered 4 more moons: Styx, Nix, Kerberos, and Hydra. Eris has its own moon, Dysnomia. Haumea actually has 2 moons, Namaka and Hi'iaka, as well as a ring system. That's very, very interesting for an object the size of Haumea, not the size of a gas giant. Makemake has a moon with a provisional designation of MK2. Gonggong has the moon Xianglu. Meteor has the moon Weiwat, and Orcus has the moon Van. I probably mispronounced so many of those names, so I apologize if I have offended your culture. Because all these names come from, I believe, gods who have to deal with the creation of the universe or death. So very, very interesting names out there. The last thing I want to clear up before we get into talking about these things in more detail is the difference between these 3 common terms: meteors, meteorites, and meteoroids. So meteors are the flashes of light that are caused by a particle of dust or rock entering our atmosphere at high speed. So the meteor is not the thing that's causing the flash of light, it's the flash of light itself. If something survives its trip through our atmosphere, then whatever lands on the ground is the meteorite. And then meteoroids are essentially meteorites before they enter Earth's atmosphere. They're just hanging out in space. Um, Meteorites were very weird for a while. We didn't really know what they were. Ancient cultures didn't really know what they were, but now we know that a majority of them are pieces of asteroids from the asteroid belt, or even just small asteroids. We even have some meteorites that are clearly from the moon or Mars that were ejected from those bodies by by impacts on their surfaces. So meteorites come from a variety of different places, but remember the meteors. Here's a little slideshow of a few meteors. The meteors are the bright streaks of light. Meteorites are the rocks that make it to the ground, and meteoroids are the things in space before they get to Earth's atmosphere. Meteor showers are an amazing thing to see. We'll talk about them in a little bit. But if you ever have the chance to see one, especially in a dark sky spot, you definitely should. They are absolutely amazing to sit and watch. All right, so here's a selection of asteroids. Let's start talking about asteroids in detail. So once again, I've hopefully made things relatively to scale. So on the left there, you see Ceres, then one of the larger asteroids, Vesta, and then a few smaller ones, but still kind of big. We got Lutetia, Matilda, Ida, and Eros. And as you can see from this selection, asteroids, their shapes vary wildly amongst them. It really depends on how large their self-gravity is. Only Ceres is large enough for it to pull itself together into a sphere. So all these smaller objects, these less massive objects, have gravities that are generally too weak to pull themselves into spheres. So there's kind of this mishmash of weird shapes. In fact, some of them are so weak that they're really no more than loosely bound piles of rubble, which is why if an asteroid ever comes towards the Earth, you want to hope that you don't get a rubble pile, because splitting that apart just essentially gives you a shotgun spray of things impacting the Earth instead of just one big asteroid, which may be more damaging. When we talk about the number of asteroids, there are very few big ones, but a lot of small ones. So maybe on the order of 1 to 5 really, really big ones like Ceres or Vesta, but millions and millions of very small asteroids, those that are less than 100 meters in diameter. They follow this sort of power law shape, where the larger asteroids, relatively few in number, smaller asteroids, tons and tons of them. Getting the mass of an asteroid is very difficult. We've only been able to do it, you can really only do it for those that have an orbiting object around them, whether it be one of our own spacecraft or an orbiting moonlet, because you need, because then you can use Kepler's third law, which we talked about way before. You can go watch that video if you need a refresher. You use Kepler's third law to get the mass of an object. So for example, on the left here, I have the asteroid Ida, and it actually has a little orbiting moonlet, which you can hopefully see right here, called Dactyl. Now Dactyl is in a relatively stable orbit. And so it's allowed us to calculate the mass of Ida to be about 4.2 times 10 to the 16 kilograms, or 0.000007% of Earth's mass. So asteroids are not massive at all. But just by looking at asteroids, we can also get the size of it, so the volume, and so we can get densities of asteroids. And the densities can vary wildly between asteroids and look similar. So for example, on the right there, I've got both the asteroids Eros and Matilda, and they both look similar enough. They're just kind of little pebbles with some craters on them. There's nothing really distinguishing one from the other. But despite that similarity in characteristics, they have different densities. So Matilda has a density of 1.5 grams per cubic centimeter, and Eros has a density of just under 2.5 grams per cubic centimeter. So they must be made up of different things. And so we know now that asteroids are actually made up of metal and rock. And those that are in the asteroid belt, in the outskirts of the asteroid belt, they are beyond the frost line for water. Remember what the frost line is. It's closer in, it was too hot for water to condense into a liquid or into ice. Beyond the frost line, it was cold enough for water to condense into ice. So those asteroids that orbit beyond the frost line can be made out of ice, can also be made out of carbon-rich material. And so perhaps if one of those asteroids collided with the Earth in the early history of our solar system, maybe it seeded the Earth with some water. Very interesting thought. A lot of people are working hard on hypotheses like that. Because meteorites are pieces or small asteroids that have made it to Earth, we can actually study asteroids in great detail. And thanks to meteorites, we have learned that there are two basic types of meteorites. We have primitive meteorites, where the technical term for them is called chondrites. And these are essentially unchanged material from the birth of our solar system. Nothing has happened to them. And their ages have been confirmed by radiometric dating. There are two subtypes of primitive meteorites. We have stony primitive meteorites, which you see an example at the top of the slide, where these are just mostly rock with some flakes of metal. And then we have carbon-rich primitive meteorites at the top right of the slide, which are mostly rock with lots of carbon compounds and sometimes some water ice in there as well. Then we also have processed meteorites, or achondrites. And these are ones part of a larger object that processed the original material. So just like differentiation happened in the terrestrial planets, where during their formation, heavier compounds sunk towards the center, lighter compounds rose towards the top, which is why, say, the Earth has a distinct crust, mantle, core structure. Same thing could happen to the asteroids, especially the larger ones. And these processed meteorites are what was left after that differentiation. So we are two different types. We have metal-rich processed meteorites, and they're mostly iron and nickel. And then we have rocky processed meteorites, which are mostly rocky basalt, like the lava plains we see here on Earth and the Moon and many other places. And there are some lessons we can learn from both these types of meteorites, primitive and processed. Primitive meteorites, because they are essentially unchanged from the beginning of the solar system, they are able to give us some clues about when and how the solar system formed. So radiometric dating has shown that they are all on average about 4.56 billion years old. So that tells us that must have been the time when accretion began, when particles were able to condense out of the solar nebula and go in and start building up to forming planets. We also know about 86% of meteorites are primitive. So even after 4.5 billion years, there's still tons of untouched material from the formation of the solar system. Nothing's happened to it. And the two types tell us about, give us some physical evidence for the existence of the frost line. Because like I said before, the carbon-rich primitive meteorites formed beyond the frost line, so they can have some carbon compounds condensing in them, as well as some water. And we've even found evidence that some of them have amino acids in them. Those are the compounds that go into forming RNA and DNA, essentially the ingredients of life. So definitely, if one of these primitive meteorites collided with Earth in the early history of our solar system, it could have brought the necessary ingredients of life to Earth as well. So very, very interesting to think about. When it comes to the processed meteorites, these meteorites have compositions very similar to the cores, mantles, or crusts of the terrestrial worlds. So these must have come from asteroids that underwent differentiation. So the metal-rich processed meteorites must have come from the cores, where all the heavy metals sunk to the center, and then that parent asteroid, was smattered to bits by a huge collision, shattering the asteroid into pieces, and some of those bits of the core have thus landed on Earth or continued to orbit the sun. Meanwhile, the rock processed meteorites must have had the same thing happen. The parent asteroid underwent a cataclysmic collision, but instead of material from the core, we're seeing the material from the crust or mantle of those differentiated asteroids, which is why they look like rocks from lava flows. We have gone on to look at asteroids in detail. We visited a few. So very recently, sample return missions have been a feasible way to study the solar system. So I've mentioned one of these before. Hayabusa 2 is a Japanese space mission, and it went and visited the asteroid Ryugu. And I believe it has already brought back material from the surface of Ryugu and is going on to explore some more asteroids. And then just recently, the NASA mission OSIRIS-REx, I believe, has just left the asteroid Bennu with a sample on board. And hopefully will survive the trip back to Earth, and we were able to study Bennu in much greater detail, learning hopefully about the history of our solar system and how it was formed. So very, very interesting results will hopefully come out of these sample return missions. All right, here is your first question of the night. Can an asteroid be pure metal? A, no, all asteroids contain rock. B, yes, it must have formed where only metal could condense in the solar nebula. Or C, yes, it must be from the core of a shattered asteroid. So pause the video, think about your answer, and unpause when you've got an answer. The correct answer is C. It must be from the core of a shattered asteroid. We talked a lot about the physical properties of asteroids, but not where they come from. I've sort of already mentioned it already before. The vast majority of asteroids come from the asteroid belt between Mars and Jupiter. Tons and tons of asteroids are in the asteroid belt. The only other large pockets of asteroids are really the Trojan asteroid, which always stays 60 degrees ahead and behind Jupiter. That's just how the natural gravitational balance between Jupiter and the sun works. Those are just places where they can pile up and stay in a relatively stable orbit. So up here at the top right, all of the white dots are asteroids in the asteroid belt, and the green dots labeled here as the Trojans and the Greeks. Those are the Trojan asteroids, obviously, that sit ahead of and behind Jupiter. Now, why are there no planets in the asteroid belt? Why is the asteroid belt even there to begin with? Well, asteroids all track there because of the gravitational influence of Jupiter. Jupiter really dominates the solar system out here. And so there are, in fact, orbital resonances that both trap asteroids there and prevent them from accumulating together to form one big planet. Here you can see at the bottom the distribution of asteroids. So on the horizontal, we've got the semi-major axis, so distance from the sun in astronomical units. On the vertical, we have the number of asteroids. And you can see these dashed lines are orbital resonances with Jupiter. So for example, this line, the one furthest to the left, says that for every 3 orbits of an asteroid, Jupiter has orbited once. That means those gravities will align and those asteroids will experience a stronger push or pull from Jupiter. So they will either be tossed out completely or sent crashing into each other, constantly disallowing them that chance to accumulate and build up a planet. If you were to actually take all the asteroids and scrunch them all up together into one big spherical body, it would probably be about half the size of the moon. So these are not, there's not a lot of asteroids in there in the asteroid belt. In fact, there's really just a lot of empty space. This is where some science fiction movies and books get it wrong, particularly Star Wars is most famous because C-3PO in Empire Strikes Back, C-3PO says, you know, the odds of surviving a trip to the asteroid field are 3,280 to 1. Although I will give them credit, that was in a different galaxy. Asteroid field was orbiting a planet. It wasn't an asteroid belt around a star. It could have been truly the odds. But that is not the odds for our asteroid belt. We send spacecraft to the asteroid belt all the time, and nothing has ever happened to them. Asteroid collisions themselves in the asteroid belt are incredibly rare. So it's really just a lot of empty space, despite all of the asteroids sitting there. All right, moving much further outwards, we are now ready to talk about comets. Comets you can think of are basically just big chunks of ice mixed with some rocky dust and maybe some complex chemicals. And so we usually just call them dirty snowballs, you know, dust sitting on top of some ice. And this sort of confirms our theory that they formed the outer solar system, where temperatures were low enough that ice was the thing that was condensing. So these objects are primarily icy bodies. Now, let us follow comets. Unlike asteroids, comets go through a lot of changes in their orbits around the sun. So let's follow a comet through its orbit around the sun. And we'll start in the very outskirts of the solar system, where here the comet is just completely frozen. And the frozen center is what we call the nucleus. In fact, here on this slide, all the images, these 3 images of comets, what I'm showing you is actually the nucleus of those comets, not the tails or anything, although there is some outgassing that goes into forming the tails. on some of these comets. As the comet starts to plunge in towards the sun, temperatures start to increase, the nucleus warms, and ices start to vaporize. They go rapidly from solid ice into gas. Some of that gas will actually drag surface dust particles away from the nucleus and form this huge dusty atmosphere, which is called the coma. The coma can actually get really, really big, oftentimes as large as Jupiter, or even larger than the sun. But it's not at all like a thick atmosphere like we have here on Earth or Venus. It's very tenuous, very sparse, but it does extend huge distances away from the nucleus of the comet. And the coma will grow as the comet approaches the sun. And some of that gas and dust will also be pushed away from the sun into tails. Now, it is important to note that the comet tails always point away from the sun, regardless of what the direction the comet is traveling in. So when the comet is falling in towards the sun, the tails will actually trail the nucleus of the comet. But once the comet loops around the sun and starts to head back out towards the outer solar system, those tails will still be pointing away from the sun, so they'll be leading the comet in its orbit around the sun. And generally, we get two distinct tails, the plasma tail or the gas tail, which is labeled here in this image. This is gas that has been ionized by the sun's ultraviolet light, and it's pushed outwards by the solar wind. Remember, that's the stream of charged particles coming out from the sun at all times. So the gas tail gets pointed directly away from the sun at all times, regardless of what the actual nucleus of the comet is doing. Meanwhile, there's a second tail, which is called the dust tail. These are small dust particles that aren't really affected by the solar wind, but they are affected by the radiation pressure of sunlight. That's right, sunlight actually does exert a force on objects. Obviously, it's way too small of a force for us to really feel it every day. But these dust particles in the vacuum of space definitely feel that force. And so we get a dust tail that extends away from the sun with a slight curve. Now, as the comet loops around the sun and begins to travel outwards, it's moving away from the source of heat. And so the temperature starts to decrease. So the vaporization declines, the coma dissipates, and the tail just completely disappears. And it goes back to being just a dirty snowball. And that's how it spends most of its life, as a dirty snowball in the outer solar system. It doesn't spend a lot of time here in the inner solar system. Those comets that do repeatedly come back, repeatedly visit the inner solar system, like Halley's Comet, don't last that long on a astronomical time scale, because they lose about 0.1% of their ice on every pass around the sun. So eventually, they'll run out of ice to even exist. And there we go, we've lost that comet. This little video at the bottom of the slide is observations from the SOHO satellite that constantly monitors the sun's ejecta of ionized material, which we'll talk about in a few weeks. But what it's surprisingly really good at is finding a type of comet called sun grazers. These are comets that come very, very close to the sun, or they just go straight into the sun. And so what this video will show you is a comet that is going to completely vaporize as it gets just way too close to the sun. So I'll play it, and it will point out the comet here in these little brackets. It'll get closer to the sun, and then we'll zoom in. And there it goes, and it's completely vaporized. We'll see it again in slow motion. And there it goes. Sadly, this is the fate for many comets around the sun. We're constantly losing them. We've seen comets break up. This is actually parts of its nucleus, parts of, not this particular comet, but some other comet, I forget which one, where its nucleus has been broken up, and we can actually watch that happen. So this is all very, very cool to see. Now, the beauty of comets is, of course, when the comet comes around, but they still have an effect on Earth even when they're not around. Because in addition to those two tails, comets also are ejecting dust particles that are just too big to be affected by either the solar wind or the radiation pressure from sunlight. And so they just kind of stay behind, marking the comet's orbit, sort of like a trail of breadcrumbs. Now, as Earth passes in to this trail of breadcrumbs into the comet's orbit, then obviously these dust particles are going to impact the Earth. But they're not dangerous. They will come into our atmosphere about 250,000 kilometers per hour. Friction with the atmosphere will make the surrounding air glow with heat, and we see the results of that as a meteor. And in fact, as we pass through the orbit of the comet, that's where all the dust is most concentrated. So this actually leads to meteor showers. Up at the top right, you can see one particular meteor shower, the Leonids from 1998. Meteor showers are named after the direction that we see all the meteors coming from. So the Leonids are meteors that appear to be coming from the constellation of Leo. I'll put the link to this website that I have on the screen here in the description below. It's a beautiful website where it will show you what meteor showers are up. And if you click on the meteor showers, it will actually pop open a new window and show you the orbit of that comet and the Earth passing through that orbit. Beautiful website. Definitely go check it out. I'll put that in the description below. Here are the meteor showers for this year, 2021. Right now, if you're lucky, if you're in a very dark sky spot, you've got about 10 more days to get a chance of seeing some Eta Aquariids. The peak has already come and passed. That was on May 5th. You might have seen about 50 meteors per hour. That ZHR column stands for zenithal hourly rate, something like that. That's essentially how many meteors per hour you would see. The big meteor shower of every year is the Perseids. You'll get to see that through late July, through most of August, where you might see 100 meteors per hour. So that's definitely the time to go to a dark sky spot and see how many meteors you can find. Very, very beautiful. I highly encourage you to go out and try and find some meteors. They're very cool to see. Now, we've talked a lot about, just like asteroids, we've talked a lot about the physical properties of comets. Now, where do comets come from? Well, most of the comets that visit the inner solar system, they seem to come from any which direction they prefer. Random directions with random orientations with respect to the other planets. And us astronomers have tracked their orbits backwards and revealed that they sometimes come from as far away as a quarter of the way to the nearest star, about a light year away. And so we think that a majority of these comets are coming from this vast spherical region called the Oort cloud, which probably contains around 1 trillion comets. Now, of course, most of them are just going to hang out in the Oort cloud. They need something to perturb their orbits a bit for them to come in towards the inner solar system. So perhaps a passing star, nearby star, perhaps something else. I really have no idea, but it's most of them are going to hang out in the Oort cloud. A smaller number of comets do stay relatively in the plane of the solar system, travel in the same direction as the rest of the planets, and we've extended their orbits backwards, and they don't really go beyond about twice as far as Neptune. So we think they come from a donut-shaped region called the Kuiper belt. You can think of this as like an asteroid belt, but beyond Neptune, just full of comets instead of asteroids. And it probably contains maybe 100,000 comets, or on that order. The Oort cloud comets probably actually originated much further in than the Kuiper belt comets, but were tossed to their current positions by gravitational encounters with the gas giants. And I'll show you an animation of a simulation to try to explain that in a little bit. I'm making you wait, a bit of a cliffhanger. All right, so that's the comets. And now let's talk about dwarf planets. And really, the only dwarf planet we know a lot of information about is Pluto. And so before I get to that, I keep getting ahead of myself. Here's your final question. Which have the most elliptical and tilted orbits? A, asteroids, B, Kuiper belt comets, or C, Oort cloud comets? So take a moment and think about your answer, and I'll give you an answer in a moment. The correct answer is Oort cloud comets. Those can come in from any which direction, any orientation. Those are going to be the most elliptical and the most tilted. All right, like I said, Pluto is the only dwarf planet we know a lot about. So really, we're just going to be talking about Pluto here for probably the next 10 or 15 minutes. When it comes to Pluto's orbit, Pluto orbits the sun once every 248 years, which of course means that we discovered it, called it a planet, and then demoted it to a dwarf planet all before Pluto even had the chance to complete an orbit. So that was a lot for Pluto in a very short amount of time. Pluto's orbit is very interesting because it is way more elliptical and way more inclined than the other 8 planets. In fact, Pluto sometimes comes closer to the sun than Neptune, although they're 3 to 2 orbital resonance. So Neptune orbits 3 times for every 2 times Pluto orbits. That keeps them from colliding. You can see from this little animation here that while Neptune, relatively stays in the plane of the solar system, Pluto is going, 10, 15 astronomical units up and down above the plane of the solar system. So it definitely does not have an orbit like the other planets. That's also a hint why it's probably not a planet. It's more like a dwarf planet. Pluto also has 5 moons. Charon is the largest. We think Charon was created by a giant impact similar to our own moon's creation. And like I said at the very beginning of this talk, we have found 4 other moons in the late 2000s, which we think are the results, it's debris left behind from that Pluto-Charon impact. And those other moons are Styx, Nix, Chimeros, and Hydra. And they're much smaller and look like deformed rocks, just like what we would think debris from a collision would look like. And here are their orbits. Hopefully you can notice that the little red dot at the very center, that's Pluto. Pluto and Charon both orbit a point outside of Pluto's body, outside of Pluto's volume. And they are both tidally locked to each other. So if you were standing on Pluto and looking up at Charon, you wouldn't see Charon rise and set. You'd see it hanging there motionless in the sky. And the same thing if you were standing on Charon and looking at Pluto. And you'd have to be on the side facing each other. If you're on the opposite side of Pluto from Charon, you would never see Charon. So they are both tightly locked to each other. They're more like a binary system of planets, which is really, really cool, of dwarf planets. And it's really, really, really cool. So now what I want to do is I want to show you what we knew about the Pluto system before and after New Horizons. So before New Horizons, of course, we discovered Pluto in 1930, but we're so far away and so dim, we don't really know much about Pluto. In fact, it was another half a century before we discovered its largest moon, Charon, discovered only in 1978 from the U.S. Naval Observatory in Flagstaff, Arizona. In fact, the top right is the discovery images of Charon. So the main blob here, I believe, is Pluto, and the smaller blob is Charon. And similarly over here, you can't see Charon anymore. We were actually unsure of what Charon was. Was it a moon? Was it just this really big topographical feature on Pluto? We didn't really know. All we knew was that Charon's orbit was synchronous with Pluto's rotation, which is why I just said they're tidally locked to each other. But it was very hard to observe because they were never more than 1 arc second away from each other. And that was just simply unresolvable for the telescopes of the time. So it took us a while to understand Pluto and Charon and the nature of those 2 objects. In fact, we discovered Charon at a very fortuitous time, because shortly after Charon's discovery, one guy, Anderson, in 1978, pointed out that Pluto's orbit would cause Charon to sweep through the line of sight from Earth for several years every 124 years. So these are called mutual eclipses, where along the line of sight, so as we're looking at Pluto, we're going to see Charon start to come in front of and behind Pluto every about 3 days, starting in 1983 and lasting until 1990. So we discovered Charon right before this was happening. We had 5 years to prepare our telescopes for these observations of these mutual eclipses. So it was very fortuitous that we discovered Charon in 1978. Allowed us to learn a lot about the Pluto-Charon system. So what did we learn from these mutual eclipses? Well, we got a good estimate of the radii of Pluto and Charon. Pluto is just a little over 1,000 kilometers in radius, Charon about half that size. We learned about the reflectivity and the colors of Pluto. Albedo is the fancy term for reflectivity, where an albedo of 1 means completely reflective. Albedo of 0 means completely absorptive. And we saw that Pluto was moderately reflective, although there were some parts that absorbed more light than others. What was shocking is that it had a relatively red color. All the moons like Saturn and Uranus and Neptune are all kind of gray. Only the moons of Jupiter, the Galilean satellites, Io, Europa, Ganymede, and Callisto, are red as Pluto. So that was very weird. That was something we have to explain. We learned a little bit about Pluto's surface composition. So by doing spectroscopy on Pluto, we learned that there's methane ice all over the surface, and that where there's a lot of methane on the surface, that part of the surface is much brighter. Meanwhile, the darker regions seem to be places where methane has been converted into more complex hydrocarbons, more complex molecules. So we learned a little about surface composition. We even made early models of what the surface features might look like. So these are some very rough models, but we knew that there was probably a more reflective polar region, maybe some darker spots around the equator, but most of it was going to be kind of a neutral gray color. So we were able to get a hint of what the surface features might be like. And we were even able to make some predictions as to what the surface topography was going to be like. We knew that any structures on Pluto couldn't be made out of methane ice because methane ice is very structurally unsound. So it would need to be sturdier materials like water ice or nitrogen ice, need to be stuff like that. We didn't think it was going to be covered in large craters, and we even thought it might have variable topography as the seasons changed on Pluto as it got relatively closer and nearer to the sun. And that's really all we knew about Pluto. That is, until New Horizons flew by Pluto in July of 2015 and took this amazing image of Pluto. It looks absolutely gorgeous. Pluto, we found, was a world full of surprises. One key feature here is this kind of heart-shaped region, often called Pluto's heart. I've also seen people draw the Disney dog of Pluto here. Fits very nicely into that. That area is what is now known as Sputnik Planitia. It's essentially just a large basin on Pluto, holding huge amounts of ices, where molecular nitrogen ice is the primary constituent. Here you can see how big it is compared to scale, the size of the state of Georgia. So this is really big, really noticeable. And what is very noticeable about Sputnik Planitia is that there's no craters, no big unambiguous craters sitting in that whole region. So it must be very young, with the age of maybe between 10 and 100 million years. And that sounds like a very long time for us humans, but on terms of planetary timescales, that is like yesterday. It is like a baby. It's so, so young. When we look at its topography in much more detail, we see it's actually composed of a bunch of what is called cellular plains covering the northern portion of Sputnik. In fact, we've got some very beautiful high-definition images here where we can see the plains are divided into these cells measuring about 10 kilometers across that actually sort of look like convection cells. So maybe there's some weird convection happening just underneath the surface. It could be that in a few decades, if we were to send another mission out to Pluto, we might see a completely different pattern here. It might change noticeably over that amount of time. But these are very, very beautiful images. These dark spots are likely glaciers kind of sitting there floating. In fact, there are these mountains, these angular mountains that are composed of water ice. And because water ice has a higher density than nitrogen ice, these mountains might actually just be floating on top of a sea of either completely frozen or partially frozen nitrogen ice. So these mountains might move around quite a bit. And you can see, even though we're not at all talking about liquid water or any liquids whatsoever, this does sort of look like, hey, there's a peninsula. And coming up here soon, there's going to be some islands. So it's just very interesting to me that, it's completely different chemistry, completely different structures here. But it all still sort of looks like Earth topography a little bit, aside from the weird convection cellular planes. But it's all very, very interesting. Pluto is certainly a world of surprises. Just off of Sputnik Planitia, there's also these weird bladed terrain called the Tartarus Dorsey, where the age estimates put it at roughly 300 million years old. And here it's mainly methane ice sitting on a more structurally sound material, just like we predicted. We also got a great look at the largest moon, Charon. Charon is not as colorful as Pluto. It's pretty gray, except for a very conspicuous feature up here that's slightly red. This is called the Mordor macula. And while the entire surface appears to be covered in water ice, we can't figure out why Mordor macula is red, just like we can't figure out why the Great Red Spot is red on Jupiter. We don't really know why the Mordor macula is red. One theory that I remember seeing is that perhaps methane is somehow escaping Pluto, only to be trapped falling onto the North Pole of Charon, where it's being ionized by the sun's UV light into more complex hydrocarbons. We're not really sure. It's still, we're still digesting all of the information that New Horizons has given us, but it's all very, very cool. A lot of people are working very hard on this stuff. And there are other things around Pluto. That's what I keep saying. That's what determined that Pluto is a dwarf planet, not a true planet. There are other Kuiper Belt objects called cubewanos that sit between two orbital resonances with Neptune, so between about 42 to 48 astronomical units out. And a portion of those are called Plutinos, because they share the same orbit as Pluto in the same resonance with Neptune. So here at the bottom left is an image of many of those Plutinos that are all sitting in the same orbit as Pluto, including another dwarf planet called Orcus. So Pluto is certainly not clear its orbit. It's not at all like the terrestrial planets, certainly not like the gas giants. It is truly a dwarf planet. And there are other orbital resonances out here in the Kuiper Belt that govern where they can orbit. So beyond the 1 to 2 resonance at 48 astronomical units is what is known as the Kuiper Cliff. Beyond the 2 Tinos, that's what they're called, the number of Kuiper Belt objects just drops off drastically. We think that has something to do with the gravitational interactions with Neptune. Neptune keeps things from being there at the 1 to 2 orbital resonance spot. So tons and tons of cool information. I've said this before, I'll say it again. Although I spend most of my time studying galaxies and star formation, I've always got time to learn about Kuiper Belt objects and the things in the outer reaches of the solar system. I find it incredibly interesting. This is that animation I alluded to earlier about how these Kuiper Belt objects form. So the Kuiper Belt objects are in green. Then we've got the gas giants. We think actually Jupiter formed slightly further out than its present day location, and Saturn, Uranus, and Neptune formed slightly further in. In fact, Uranus and Neptune, we think, formed in opposite positions. Uranus forming further out, Neptune further in. But through some gravitational interactions, Jupiter moved further out, moved further in, causing the other planets to move out, scattering those Kuiper Belt objects, switching the positions of Uranus and Neptune, and pushing many of what was in the Kuiper Belt objects into the Oort cloud, leaving behind the relatively few Kuiper Belt objects we see today. This is called the NICE model, N-I-C-E, in case you want to go read up on it. I'm not going to get into any of the heavy details of it. I've learned that mistake. So you can go do that reading on your own. Now, obviously, that switcheroo that the outer planets did sent a lot of those Kuiper Belt objects going every which direction. And so that leads us to the topic of cosmic impacts, which happened a lot in the past, happen much less frequently nowadays, but they still do happen. Famously, the comet Shoemaker-Levy 9 broke apart under Jupiter's tidal forces in 1992. Up at the top right, you can see the 21 distinct pieces that its nucleus broke into when it got too close to Jupiter. And then almost exactly 2 years later, it fell into the planet. So this little infrared image shows a bright spot appearing. That is one of the impacts. The other big bright spot, that's the moon Io. We don't have to worry about that one. But as these comet pieces crashed into Jupiter, they left behind these black scars on the cloud tops of Jupiter that were often more visible than the Great Red Spot. Because each of these impacts was as strong as 1,000,000 hydrogen bombs each. So if this were to happen on Earth, you could tell it'd be incredibly devastating. In fact, that's what we think happened to the dinosaurs. Back in 1978, the father and son duo, Luis and Walter Alvarez, were analyzing some soil samples in Italy, and they found this thin layer of sediment that was deposited around 65 million years ago. Now, and you can see this dark layer here that the hand is pointed to. That is the layer they discovered. And that layer was rich in iridium, which is a rare element on the surface of the Earth, but very common in meteorites. And they kept looking all over the world, and all over the world, they found this same layer dated to 65 million years ago. This layer is also rich in other metals like gold, platinum, osmium. There's some shocked quartz, which are quartz crystals with a structure that indicates they experienced high pressure conditions of an impact. There's spherical rock droplets of a type known to form when drops of molten rock cool and solidify in the air. And even in some places, soot that appears been produced from forest fires. And these are all the signatures of an impact by a meteorite measuring about 10 kilometers across, resulting in the Chicxulub crater just off the coast of the Yucatan Peninsula in Mexico, which is a 200-kilometer wide crater. You can see it here in this gravity anomaly map, which measures the slight variations in the change of Earth's gravity. And you can see this kind of circular region. The white line is the coast of the Yucatan Peninsula, so it's half in, half out of the water. It's really only visible this way. You can look at the ground there, and you don't really see a visible crater mark, but we do have signatures that there is a crater there. When this crater impacted, I do want to read you this of what happened when this meteor impacted the Earth. It apparently hit at a slight angle, sending a shower of red-hot debris across the continent of North America. A huge tsunami sloshed more than 1,000 kilometers inland. Much of North American life may have been wiped out almost immediately. Not long after, the hot debris raining around the rest of the world ignited fires that killed many other living organisms. The longer-term effects were even more severe. Dust and smoke remained in the atmosphere for weeks or months, blocking sunlight and causing temperatures to fall as if the Earth were experiencing a harsh global winter. The reduced sunlight would have stopped photosynthesis for up to a year, killing large numbers of species throughout the food chain. Acid rain may have been another byproduct, killing vegetation and acidifying lakes around the world. Chemical reactions in the atmosphere probably produced nitrous oxides and other compounds that dissolved in the oceans and killed marine organisms. Adding insult to injury, some evidence suggests the impact site was rich in carbonate rocks, so the impact may have released large amounts of carbon dioxide in the atmosphere. The added carbon dioxide would have strengthened the greenhouse effect, and the months of global winter may have been followed by decades or longer of global summer. Perhaps the most astonishing fact is not that 75% of all species died out, but that 25% survived. Among the survivors were a few small mammals. These mammals may have survived in part because they lived in underground burrows and managed to store enough food to outlast the global winter that immediately followed the impact. The evolutionary impact of the extinction was profound. For 180 million years, dinosaurs had diversified into a great many species, large and small, while mammals, which had arisen at almost the same time as the dinosaurs, had generally remained small and rodent-like. With the dinosaurs gone, mammals became the new kings of the planet. Over the next 65 million years, the mammals rapidly evolved into an assortment of much larger mammals, ultimately including us. However, that's not the only impact in Earth's history. There have been even more recent ones than the ones that killed the dinosaurs. Both of them, oddly enough, happening in Russia. So maybe don't go to Russia if you want to avoid being killed by an asteroid. One very famous one happened in 1908, where there was this tremendous explosion that happened over the Tunguska region in Siberia, where entire forests were flattened and set on fire, and air blasts were flattened people over 200 kilometers away. Seismic and air disturbances were even detected as far away as Washington, D.C. And yet, this explosion released energy probably equivalent to several atomic bombs, but was caused by a relatively small asteroid, no more than 40 meters across. Thankfully, atmospheric friction caused it to explode before impact. And even more thankfully, it happened over a non-populated region. If it had happened over, say, London or New York City, it would have been the worst natural disaster in human history. One that got very close to that was the Chelyabinsk meteor in 2013, also in Russia. In contrast to the Tunguska asteroid, this asteroid was only 20 meters across. And thankfully, it also detonated midair with the force of a 500 kiloton nuclear bomb. Probably very frightening to the people watching that morning in Chelyabinsk. So these collisions still happen. And so I've got some good news and some bad news. The good news is that dinosaur killers are incredibly rare. They probably happen on the order of tens of millions of years. Here you can see in this plot, I've got on the horizontal the impactor size, ranging from 1 meter on the left to 100 kilometers on the right. On the left vertical, I've got the time between impacts. And on the right vertical, I've got the relative number of asteroids. This isn't a hard and fast number. But you can see that for really small meteor, really small impactors, Earth gets hit by them probably once a month, and yet we don't even notice. Meanwhile, the dinosaur killers, those that are, 10 kilometers, 100 kilometers, those happen maybe every 100 million years, maybe even once in a planet's lifetime. And there's relatively few of them, maybe only 1,000, a million of them. Meanwhile, for those that impact us every month, the really small ones, there's probably 1 sextillion of them, around that number. So the bad news is that Tunguska asteroids are incredibly common and probably impact the Earth every couple of 100 years or so. So we really got to think about protecting the Earth, diverting asteroids from colliding with us. And we're getting really good at detecting them, but there's still some work that needs to be done. So I will leave you with that lovely thought tonight. So just like that, we are done talking about our solar system. But next week, in a few days actually, because this is so late going up, we'll be talking about exoplanets, planets around other stars in our galaxy. And then we'll start talking about relativity and getting into stars and galaxies, which is really where I spend most of my time thinking about. So comment down below if you're enjoying these. Let me know if you have any questions. Make sure to like, comment, and subscribe to all the YouTube things. And I will see you all next week.